this planning question is about cyclopentene and piperylene, which has the same molecular formula C5H8. So henceforth, they are actually isomers. They both exist as colorless liquid in room temperature and pressure. Okay, now change this. Okay, the density of cyclopentene is 0.771, whereas for piperylene, it is 0.683 grams per cm cube. Okay, so you're supposed to give the IUPAC name of piperylene. So piperylene is not following the IUPAC name. So in this case, if we go back to what we have learned about prefix, stem, and suffix, there's no prefix in this case because there's no substituent. It's only made out of carbons and hydrogen. So the longest carbon chain, there are 5 of them, so that would be a pent. And the principal functional group, it's alkene, so there will be an ene. However, due to the presence of 2 alkene, that will be the naming of diene in this case. And we'll be looking at the positioning of the double bond. Okay, so the longest chain of 5 has double bond with the lowest number 1 and 3 respectively. So in this case, this will be called 1,3 pentadiene. Okay, quite a number of you wrote 1,3 pentadiene, which is not correct because it's a linguistic thing that you have to put penta. It can also be named as penta 1,3 diene, okay, and not pent 1,3 diene. So take note of that. Okay, and the question wants you to write equations. So it says that the liquid is labeled with C5H8, which you are not sure which is the specific identity, whether it is cyclopentene or piperylene. So in this case, the technician has to perform an experiment to determine the number of carbon-carbon double bonds by titration. Okay, so it's titrating with bromine dissolved in CCl4, which we have learned this before. In such a case, the two equations for cyclopentene and piperylene would be as such. Okay, for cyclopentene, there's one double bond, and we know that double bond can react with Br2, and in such a case, this is an electrophilic addition, which adds a Br across the double bond. Okay, and this is balanced. Okay, so just take note that you cannot write condensed formula because we want to know the exact compounds. Okay, so that's the first point that we avoid. The second thing is that you cannot write a linear way of structural formula for a cyclic compound. Okay, so in this case, you have to draw out the structure. Okay, moving on, we will look at piperylene. So piperylene is a straight chain, okay, with 2 double bonds. It will react with Br2, and some of you were a little bit confused in terms of the fact that you think that there's only one Br2 being added across, but when there are 2 double bonds, you can't tell which is more reactive or not. So you can't, if you were to use one double bond to react, why is it this double bond rather than the other one? So that is something that can't explain. In such a case, what happens is that the alkenes, they will be able to react. That's what we have already learned. So both will react, and in this case, this would be the structure. Okay, on each of the carbon of the double bond, a Br will be added on it. So this is the compound that you should see. Okay, so that is for the equations. We're going to move on to the planning questions, which you need to plan an experiment to determine if the bottle of C5H8 it's cyclopentene or piperylene. And what we know is the difference based on the fact that the amount of bromine that's required is different. Okay. And if the amount used is different, this would mean that the volume of Br2 used will be different as well. And this is the most important idea that you need to have in order for you to get the final correct answer. Okay, so let's look at what we are provided with. We are given 6 moles per dm cube of Br2 and CCl4 and the other standard apparatus in the lab. So you're supposed to include the volume of C5H8 and you need to show appropriate calculations. Following that, you would then give the usual titration procedure and then measures taken to ensure reliability of results, which quite a number of you did not show that. And finally, you are also supposed to briefly describe how the data that you have suggested would help to identify the identity, to help to identify what exactly is the C5H8 in the sample bottle. Okay, so in such a case, in these bullet points, they are all very important and you need to make sure that all the points are being fulfilled, and including the last point that does not have a bullet as well. So usually the bullet points are sequential, meaning that you should answer one followed by the other. It guides you through the entire planning. So in this case, we need to suggest an appropriate volume of C5H8 and to suggest what should be the correct volume. And quite a number of you suggested 25 cm cube because that's the usual volume that we use with a pipette. However, in such a case, you will realize that this will not work because there will be some consequence due to the capacity of the apparatus. Alright, so in this case, since the question wants you to suggest the C5H8 used, you have to consider the fact that for titration, which is the apparatus that you can control the amount, the volume of the species. And in such a case, we can't control how much solution we add into from the burette into the conical flask because it depends on the end point. So which means that if I'm supposed to decide a volume of C5H8, the apparatus that would have a fixed, that can define as a fixed volume, would be the solution in the conical flask. Okay, so whether the identity is cyclopentene or piperylene, I'm going to decide on a certain volume, and in such a case, I would show the calculation using 25 cm cube and prove that why it is not a suitable volume to be used. Okay, so I would show this calculation. Okay, so if 25 cm cube of the unknown C5H8 is used, okay, so the first possibility is that it would be cyclopentene. Okay, and what it means is that I have to make use of some data to do some form of calculation, and what I would see is that I've got the density of cyclopentene, which is 0.771, which is something that I can do some calculation. So in this case, I can actually find out the mass of cyclopentene, which is 25 times 0.771. Okay, and then the amount, I can also decide on that, and I'll do some calculation. Okay, so the mass would be 19.275 grams. And to find the amount, it would be divided by MR, which in this case would be 68. And that would give you 0.2835 mole in 4SF. And we will continue with some form of calculation. In such a case, if I've used 25 cm cube of cyclopentene, I also can find out that based on the equation that I found in the previous part, okay, cyclopentene and Br2 is 1:1. Okay, which means that the amount of Br2 that is required is also 0.2835 mole. And that would mean that I can know that if I were to use 25 cm3 or C5H8, the volume of Br2 would be equivalent to the amount divided by the concentration, and that will give me 0.0472 dm cube. That works out to be 47.20 cm cube. Okay, this endpoint is pretty high, but kind of still acceptable because it's still within the capacity of the burette. But what you would realize that the one that violated the calculation in terms of the capacity is if it were to be piperylene. Okay, so same thing, if 25 cm cube of piperylene is used, I would do the same set of calculation using the specific value relevant to piperylene. Okay, in this case, the density of piperylene is 0.683. That will give me 17.075 grams. Okay, the amount of piperylene, okay, would be the mass divided by the same MR because they are isomers. Okay, which is 0.2511 mole. Okay, in this case, the amount of Br2 is no longer 1:1 because for piperylene, we know that the ratio is 1:2. So for Br2, I would have to multiply by 2. Okay, in that case, the volume of Br2, its amount divided by concentration, which quite a number of you did not use the correct formula, which is why you got a different interpretation. Okay, and in this case, the volume is way too high, and that is not sensible and not logical because it's beyond the capacity of the 50 cm cube burette. Okay, so in such a case, it would suggest that whatever volume that is suggested over here is not very logical. So I'll think of another suitable volume that I can add into the conical flask. And since when we transfer solutions to the conical flask, it would be actually from the pipette, and the usual volume is either 25 or 10. So since 25 doesn't work in this case, I want something smaller. 10 cm cube would be the natural next option that I will look at. So I'm going to change this to 10, and I'll change all the calculations accordingly, and we'll see how things change. Okay, the steps to do is exactly the change. Is exactly the same, but I'm just changing to suit the new volume that I use. Okay, so for cyclopentene, if it's 10 cm cube, you would be using 18.9 cm cube of Br2 at the end point. So I'll do the same to change that for piperylene. Okay, so insert the 10 cm cube as well, and we'll see what happens. Right, so in this case, it would have a value that is 33.50 cm cube or 33.48 more relevantly, but in this case, a burette can only read to the nearest 0.05, so I record it as 33.5. So this is perfectly fine because both values over here, 18.9, whether is it piperylene or cyclopentene, whatever endpoint it is, it's still within the range, and therefore this is a suitable volume that I should be using. Okay, so that's how we decide on that, and with that decision I can move on with writing the steps for the titration procedure, and that will be quite standard. So what happens is that you have decided on 10 cm cube, so you use a 10 cm cube pipette. You transfer the solution which is the unknown C5H8 solution into a clean conical flask or clean and dry conical flask. Okay, and after which you would fill the burette with Br2 in CCl4. There's no need to fill it to the 0 cm cube just to reinforce again, because sometimes if the endpoint is not so large, whatever you're provided with may not be able to allow you to fill it to the 0 cm cube mark. So you just have to mention that you have to fill the 50 cm cube burette with Br2 in CCl4. And just take note that you are not supposed to add any indicator in this case, because if one of the species in the conical flask or burette is capable of undergoing a change in color on its own, there's no need for you to add in any indicator. And in this case, Br2 will actually will observe a difference in color when the reaction proceeds. Okay, so we'll continue. So after you fill that, you can start your titration. Okay, so you titrate the solution against Br2, okay, and you're supposed to add dropwise near the end point as per usual. Okay, you would do so until the color changes, and you need to specify the color change. In this case, we are always observing the color change in the conical flask, which we know that this is C5H8 at the start. And question has already mentioned that this is a colorless solution, which means that before you add in any Br2, it should be a colorless solution. And now you realize that once all the Br2 is required has been added, any excess would turn the solution brown. Okay, and we'll say that it will turn permanent brown. Okay, so that's the endpoint and not the other way, so just take note of that. Okay, you will proceed with recording the to record the burette readings. Okay, and as per usual, you repeat the titrations to obtain 2 consistent readings, and you should write down the correct range to decide if it's consistent or not. Okay, and the range would be plus minus 0.1 cm cube. Okay, and with that, I have already answered the first point, which is the volume that I use, that is 10 cm cube. I have included the essential details of the titration procedure. I need to move on to look at bullet point number 3, which is the measures that you take to ensure reliability of results. So some measures to take is that you must also make sure that there's no other possible reactions from happening. And this is what we have learned for Br2. We have learned this reagent in both alkanes and alkenes. So this is something that concerns alkenes, which we use Br2 in the dark. So in that case, for alkanes, which is something that you can see in part of cyclopentane, those carbons with single bond hydrogen, all right, which means that So over here, okay, example, this carbon, this carbon, and this carbon, they are part of the alkyl chain or the alkane, so they are actually capable of undergoing free radical sub in the presence of UV light. So this is something that you want to avoid, and that is something the same over here on the carbon of this piperidine, which can also undergo free radical sub in the presence of UV light. So in order to ensure the reliability of the experiment, you need to make sure that the titration was carried out away from sunlight. Okay, and you need to also recall that for free radical sub, other than sunlight or UV ray, it can also be conducted if you have sufficient heat. Okay, so you need to avoid sunlight and heat to avoid side reactions such as free radical sub. Okay, otherwise it will interfere with your results and you may not be able to accurately decide if it is cyclopentene or piperylene in this scenario. Okay, and moving on to the last thing that we need to solve, which is that you need to make use of the experimental data. You have conducted the titration. How would you then decide on the identity of C5H8, which is actually based on the calculations, it helps us to decide. There's no need for you to do any more calculation for mole. You conducted the experiment, you have recorded down the burette reading. So based on the burette readings, we know that the one that is nearer to 18.9 would have to be cyclopentene, whereas if it's 33.5 thereabout, it will be piperylene. So that's how we decide on the identity of the unknown C5H8. So you just need to mention that if the average title is closer to 18.9 cm cube, the sample contains cyclopentene, while if the average title is closer to 33.5 cm cube, the sample contains piperylene. Okay, so that would sum up the 4 points that we want, and that would give you the 8 marks for this question. So it's not actually difficult, but you need to understand what is the species that should be placed in the conical flask, some procedures, and to set you into the situation on what is a suitable volume. So always the capacity of the apparatus is an important criteria and consideration for you to take note of. Okay, and last part to this question, it asks about a potential safety hazard in this experiment and state how you would minimize the risk. So in such a case, when we are looking at safety hazard, and once we have identified that it consists of an organic compound, okay, we will always use this as the safety hazard, which is that all organic compounds, they are generally flammable, and that is a safety hazard. Okay, so how will you minimize this risk? You would make sure that there's no direct flame around the organic compounds, and that will prevent an explosion from happening. So we'll just say that ensure that there is no direct flame in the vicinity. Okay, and that would be what we require for part D's answer.